In this video lecture, I'm going to continue my previous lecture on DC machines, the number one presentation. In that lecture, we basically understood the basic structure of DC machines. Um, we said that we first look at the classification of electric machines. We said that there are DC machines and AC machines and also some special machines. So under DC machines there are other categories like self-excited, separately excited, and then self-excited, series, shunt, compound, like that. So after that we looked at the uh, construction of DC machine, mainly the stator, the stationary part, and the rotor, the moving rotating part, and then the commutator, which is acting as AC to DC mechanical converter. uh, then we have brushes which will supply the current to the rotor rotating coils. uh, So then we looked at the construction of uh, commutator, right? Uh, and also the stator, and then the rotor, and the commutator, and the brushes. So, we basically understood uh, how a DC machine is assembled. Uh, so here we have the rotor, rotating part, with slots which holds the internal coils, um, and then we have the commutator which supply the current to the rotating coils, and then we have the stator around the rotor, which is providing the magnetic field required for the rotation, or uh, or required for the electrical generation, right? So then we were talking about windings. uh, if there are small windings, we said that we can wind the coils onto the stator using either machines, automatic winders, or manually we can do that. But in the case of large machines, um, coils are connected and then inserted into the armature slots. Uh, then I will continue from that point onward uh, regarding the windings. Mainly the terms first. Uh, a winding is consisting of turns. So turn is actually one loop of current. That means it is having conductors, mainly two conductors interconnected via end connectors, right? So these conductors are effective in machine for either rotation or generating EMF. Then several turns together is called a coil, right? So when you have many turns, then it becomes a coil, and then several coils together will form a winding like this, right? And then there are basically two types of windings. One is called lap winding and the other one is called wave winding. uh, so the difference is that the way the armature coils are connected to the commutator, right? So in lap winding, the finishing end of one coil and the starting end of adjacent coil are connected to the commutator segment under the same pole, right? So starting of uh, the finishing end of one coil, the finishing end of this coil and the starting end of the adjacent coil are connected to the same commutator segment under the same pole. The lap winding is used on low voltage, high current applications, low voltage, high current applications such as starter motors on vehicles. So this explains how the windings are done on lap winding. The external power supply, the DC supply, is given to the rotor through brushes and the commutator. So basically when you look at how they are connected, there are several parallel paths, parallel coils like this between the supply, right? So the number of parallel paths, we use the letter A, is always equal to the number of poles and also to the number of brushes. So in this case there are 4 brushes here and also 4 poles here. So A equals to P in case of lap winding. Now if we look at the wave winding, the two ends of a coil are connected to the commutator segments. So the two ends of a coil are connected to the commutator segments that are separated from each other by approximately 360 electrical degrees. That means 180 mechanical degrees. So so one end is going through the armature slot and then go to the other side, and it is connected 180 degrees mechanically apart, right? So so this wave winding is suitable for high voltage low current applications, right? So here the top coil side is shown as solid line and the bottom coil is shown as the broken line. So not like in the lap winding. In lap winding, this coil end comes here and connected to the next one. So but here it is connected to 180 degrees apart mechanically. That is on the other side, opposite side of the rotor, right? So this is how they are physically connected. So in the case of wave winding, the number of parallel paths is always equal to 2. So there are only 2 parallel paths, and there may be 2 or more brushes positions. So a wave winding A is always equal to 2. So there is a relationship between this number of commutator segments and number of poles, etc. But at the moment I am not going to explain those things, but we will touch upon these calculations later. So for the time being I will skip this slide. Then let's look at the operation of DC machines. First we will consider the motors. When we say motor, it basically convert electrical energy to mechanical energy. Uh, Here the field poles are supplied by DC excitation current, which creates a magnetic field. Or sometimes it could be permanent magnets. If it is electromagnet, then the field poles are supplied with DC excitation current. Then the rotor coils are supplied by DC current through brushes and the commutator. The interaction of magnetic fields and the rotor current generates force called Lorentz force that drives the motor. So the direction of the force can be known by Fleming's left hand rule. So in this case, if you take your left hand and keep your thumb, first finger and the second finger perpendicular to each other, then the second finger is directed towards the current direction on the conductor, and the first finger is directed towards the magnetic field. Then the thumb will give us the direction of the force uh, on the conductor, right? And the magnitude of the force is proportionate to the magnetic field strength, the current through the conductor, and also the length of the conductor. So F equals BI/L. So this is regarding motors. The other type of DC machine is called the generator. Uh, so in the generator, what we have to do, we have to rotate the rotor by using external force. Uh, Maybe it is the force is taken by a combustion engine or hydroelectric turbines or windmills, etc. Uh, then when it is rotating in a magnetic field, it will generate uh, some EMF. But this generated EMF is alternating type. That means alternating current is generated. But if you want DC as the output, then we have to rectify that using the commutator, right? And the direction of the EMF generated can be found by the Fleming's right hand rule. Um, Again, the middle finger is representing the current, the direction of the current or the EMF generated. First finger points towards the magnetic field, and the thumb is pointing towards the direction of motion or direction of speed of the uh, coil, right? So the magnitude wise, the generated EMF is proportionate to the magnetic flux density, the length of the cable, the length of the conductor, and the speed that it is moving. Uh, and remember the flux density. When we say flux density, it is the flux that is perpendicular to the conductor, right? So and if you look at the generator in more detail, uh, when the coil is rotating, it cuts the magnetic flux produced by the field poles, um, and consequently the EMF will be generated in the coil, which is equal to BLV. That means it is the EMF generated is proportionate to the strength of the magnetic field, the length of the conductor, and the speed of the movement. And then you will find that at this location, when the coil is at this position, it cuts the maximum amount of flux lines, uh, because the conductor here is perpendicular to the magnetic flux. So actually the magnetic field is uh, in horizontal direction, and this line is perpendicular, this I mean the conductor going into the screen, right? Is actually the coil is like this now. If I try to do something here, actually the coil is going like this, right? So this bar is perpendicular to the magnetic field here. So so this is the position where it erase this. Why it's not erasing? It doesn't matter. Right, okay. So uh, at this position it cuts the maximum number of field lines, so it the EMF generated is maximum at this position. But when it is rotating and then it comes to this location, it is the at this point the conductor is moving parallel to the magnetic field. Therefore actually the magnetic flux that is cut by the conductor is 0 here, so therefore no EMF will be generated. So that is why the EMF is becoming 0. So at here you get the maximum and then gradually decreases and goes to the 0 at this point. And then what will happen, now this conductor was earlier moving down and now it is moving up. When it passed this point, it's moving up, therefore the EMF generated will be reversed, therefore it is shown as negative here. So the EMF generated is a sinusoidal waveform like this, which is alternating, right? So if you need this as a DC current, then you have to rectify it using the commutator like this. So here in the commutator there are two segments of this commutator which will change the direction of the current supplied to the coil when it is passing this particular location, right? So it is making sure that the direction of the current is such that uh, uh, it is giving the same EMF throughout. So the output now you are getting is like full wave rectified AC signal. So basically the generators could be AC generators or DC generators. If you want AC signal as out, then you have to connect the coils into the external circuitry or the load by using slip rings like this. Slip rings means they are complete rings, so continuously it is taking the current out from this one, uh, therefore it changes the direction according to the change of the direction of the induced EMF. If you want DC as the output, then you have to use a split ring commutator. That means the ring is now split into two. Therefore, when it is rotating, the direction of the current flow will be automatically reversing. Therefore, all the time what is coming out from these two rings, the split rings, becomes DC. So we can calculate EMF by using the E equals BLV relationship. So that is we have actually the L is the length of the conductor, so E equals BLV can be applied only a single conductor. But in the case of winding, rotor winding, there are so many turns and so many windings. Therefore, we have to adjust, or we have to calculate the EMF accordingly. So in that case, if the coil is rotating in omega m radians per second, we can find the generated EMF by using the formula that we are going to derive here. So if it is a single turn, it will be BLV, but there are two turns in one coil. Therefore, for a single coil, the generated EMF will be 2 times BLV, where V is equal to omega R if it is rotating at omega angular velocity. So in that case, you can apply here 2BL omega R, and this is only for one turn, but if there are so many turns, you have to multiply it by number of turns as well, right? So the magnetic flux density, which is called B, is actually the total flux divided by the area of the pole, right? Uh, by assuming uniform field distribution on the pole, we can find the average flux density by just dividing flux by the area of the pole. Then phi over A, where this A means uh, 2 phi R into L divided by P, where P is the number of poles, right? So then we can find the EMF generated by single pole as ET equals, this is coming from the previous equation where ET equals 2 times BLV. This is 2 times BLV. This is for single turn, but you have so many turns, and V equals omega R. So by using that formula, you can find the EMF generated by a single turn as P phi over phi into omega m. So the overall armature winding, if you consider, which consists of Z turns, you can find it as the total EMF generated is equal to Z into ET. Then Then if there are uh, several coils like that, I mean several paths, a number of paths is A, uh, then for single path, then overall uh, voltage will be we have to divide that by A, so you get this equation EA equals ZP phi omega m over A into phi. So in generator EA equals induced voltage, in motor EA equals the back EMF. So therefore for a normal DC machine, armature voltage is written as Ka into phi over omega m, where the K is a constant known as the armature constant, which is equal to number of poles into number of turns coil divided by number of parallel paths divided by phi. So the induced voltage can also be expressed in terms of speed of the generator in revolutions per minute. Uh, so so this actually has converted omega m into revolutions per minute, because normally for motors machines the revolutions per minute is shown, not the revolutions per second. So that conversion has happened here. So this is giving either the back EMF generated in case of motor, or the normal induced voltage in the case of generator. So the back EMF is related to the fact that the armature coils that are moving under the effect of the force that is due to the armature current in the case of motor. These same conductors, while moving through the magnetic field, have a voltage induced EMF in them. So that means when the motor is working, the rotor coil is rotating in the magnetic field. So due to this rotation, it will generate some EMF. So that is what we call the back EMF. So so while the machine is running as a motor, part of it is still working as a generator as well. So the back EMF is opposed to the applied voltage, and the back EMF is only present when the motor armature is moving. When it is steady, then there is no induced EMF. The induced EMF can never be equal or greater than the applied voltage. So I think with that we can wind up this presentation, but there are some few more slides here which calculates the torque and all, but we will come to that part later. So I will skip these slides for the moment. So for you to understand this concept better, I will show you a small video clip so that you can have a real or the practical meaning or understanding how a DC machine is working. So let me open up that video.
in toys, appliances, and radio.
Right. Uh, so now let's look at this video.
Motors convert electrical energy to mechanical energy with the help of magnets. DC motors are one type of motor and are often used in toys, appliances, and radio-controlled cars or boats. In this simple motor, powered by a battery, the electrical current and magnetic fields make the motor's armature or rotor rotate continuously. To understand this better, we'll look closely at these forces and how they interact. First, we activate this circuit. While electrons actually run from negative to positive, the convention is to think of electricity going from positive to negative, so that's how we show it here. The charged particles in the electrical current create a magnetic field around them as they move, as shown by these blue arrows. Because the copper coil, that is the armature, is part of the circuit, the current also creates a magnetic field around the coil. By passing current through this coil, we've turned it into an electromagnet. As you can see from the way the magnetic field lines in the coil converge, this electromagnet has a north and a south pole, just like a permanent magnet. The electromagnet's field is represented here by a bar magnet. This isn't much of a motor yet though. An important piece, an external magnetic field, is missing. In our demonstration, this horseshoe magnet will provide that field as shown by these blue lines. We position the horseshoe magnet so that the rotor is right in the middle of the magnet's field. Let's power the circuit again and watch in slow motion what happens between the poles of that magnet. As soon as that current, represented by the red arrows, starts running through the armature, a magnetic field forms around it. Stopping the action for a moment to take a closer look, we see that the field around the coil opposes the field of the horseshoe magnet. Using this bar magnet again to represent the field of the coil, we see here that the horseshoe's magnet's north pole is attracting the south pole of the electromagnet in the armature. In fact, these two magnetic fields oppose or attract each other at several points. Let's talk about how the design of a DC motor leverages these two forces into a machine that can do endless types of work. The current that runs into the armature passes first through one of these graphite brushes, then through one of the two semicircles that make up what is called a commutator, which is a rotary electrical switch made of copper and featuring two gaps. The cleverly designed commutator is key to making the DC motor work. To see why, we'll temporarily replace it with this copper ring, which has no gaps. The bar magnet again represents the magnetic field generated in the coil. As you see, this is still not much of a motor. The interacting magnetic field caused the armature to move, but only to the point when their fields aligned north to south. And there they stayed, opposite attracting opposite, two magnets stuck together. Let's return the real commutator to its rightful place and see what happens now. Notice how one half of the commutator connects to one arm of the armature while the other half connects to the other arm. The current enters the first arm, making the coil spin. But this time, just as the commutator reaches the halfway point of its first cycle, a brush reaches the first gap. After jumping that gap and making contact with the other half of the commutator, it sends current through the other arm of the armature. As a result, current is sent through the coil in the opposite direction. This reverses the polarity of the electromagnet created by the powered armature. So once again, opposites attract, likes repel, and the armature turns another half rotation. As explained by Fleming's left-hand rule, the interaction of the magnetic fields will keep the rotor spinning and spinning for as long as there is current.